In this video, we're going to be doing a Mathematical Reasoning FRQ. So let's start off with this. We have a bar of length L can rotate with a negligible friction about a vertical axle at the bar center. As shown in the figure, a dart mass of md is traveling horizontally and perpendicular to the bar with a speed v initial as indicated. The bar is initially at rest and then rotates after the dart hits and sticks to the ball at a distance r from the axle. The bar has a mass mb and rotational inertia ib about its center. So we know that, okay, so figure 2 is a top view of the bar during the brief time interval that the dart is colliding with the bar. The two dots in the figure represent the locations where the dart hits the bar, and the bar's center of mass. So we are asked to create a free body diagram. Well, we can just draw the free body diagram. We have our mg here, of course, and yes, that's just going to be our mg. When the dart hits, it's also going to have an mg as well. Oh, wait. After the dart collides and sticks to the ball, the dart ball system rotates and the dart collides, and the dart moves in a circle with the speed vf. So this is an inelastic collision, perfectly inelastic. So starting with angular momentum, derive an expression for vf in terms of physical constants. What we're going to do is we can start off with a calculus idea, which is the summation of torque external is equal to dl over dt. And during this very short collision, the net external torque about the axle is going to be equal to 0. So summation of, or we're going to just use torque. So we have L initial, LF, we have conservation of energy, right? And what we can do is we are going to take this and we are going to find our initial. So initially we have R, and we only have the dart with angular momentum about the axle. So only initially the dart is having a angular momentum here. This is going to be at rest, and this is moving. And it's based off of mv, right? So that means that this is not moving. Therefore, that would be m times 0, right? So that's why your bar's momentum is 0. Now here, we're going to have r md v1 is equal to, because angular momentum is mvr, right? So you're going to have mdvr, and then this is because the dart's momentum is going to be perpendicular to the radius. So this is perpendicular to radius. So this is our angular momentum initial. What about our final? Well, to find this, we know that we have to find our total inertia post-collision. This is going to be the inertia of b plus m dr squared. We know that this will be equal to I total omega. So we'll just sub this in. And we'll set this equal to our final. Now we have to relate the speed of the dart to our final speed. So when you have this setup, we are going to have v final is equal to omega r. And if we solve for omega, we're going to get omega is v final over r. We'll substitute this in for where we see our omega here. And we substituted this in over here, by the way. So this is going to turn out to be md now you multiply both sides by r. And then for VF, we get this. So the dart's initial angular momentum becomes the rotational angular momentum of the combined dart system. Now, figure 3 shows a top view of two non-uniform bars, bar X and Y, that can each rotate with negligible friction on the vertical axles about their center, similar to the original bar. So both X and Y are initially at rest, same mass. However, the mass is distributed differently in the two bars, which is obvious because we can see their shapes are different. Bar X has more of its mass located near the center of mass, and then bar Y has more of its mass located near the ends of the mass, as shown. And then identical darts are launched at either of the bars, as in the original situation, figure 1, with a dart hitting each bar at the same velocity at the same distance from the bar's axle. The darts collide and stick to the ball perfectly in elastic collision, after which the bar X system rotates with an angular speed omega x, and the bar Y system rotates with an angular speed omega y. Now we want to compare the two angular speeds and which one is greater than the other. So what we are going to have is going to be this option, because we can see that if we use angular momentum, we have that for the same angular momentum. So for same L, the object with smaller I rotational has the larger speed. It makes sense because if you hold L constant, right, and you want to just have a decrease in I, that is going to have to make omega increase to compensate. For example, if you have a really low I, like 1, and then you still want your whole entire angular momentum to equal to 10, right? You're going to have to multiply this by 10 in order, a really large number. So that means your speed has to be really big in order to remain equal to 10. So that's an example. So we know that for X, we can see that it has more mass near center, which means that it's going to have a small I. And for bar Y, it's going to have mass near end, so that it is going to have a large I rotational. So it has a large resistance to motion because it's very far away. However, for this bar where all the mass is in the center, it's very close and it doesn't have to go very far in order to move the object. It's all very close to the center of mass, the place where it's going to begin moving around in a circle. So yes.